So as Hogg said, you guys pretty much know me already. And so the things on this slide are probably what you know about me right now. I do like to observe. I've racked up over 100 nights of observing in my time, but these days I mostly use public archive data. But I do know and love the data very closely. I like to develop open source code, and that's something that I've really learned a lot about how to do here at CCA. That part of my work has grown enormously in the last year and a half, and I'll tell you a little bit about that. I also like to use large catalogs. I've done quite a bit of work on Gaia DR2, a lot of it with many of you, including a paper that Lauren and Chiara and I wrote about finding pulsar companions that you may have heard about from Chiara before. I did a cross-match catalog between Gaia and all of the Kepler and other exoplanet host stars. So I like to play with data on a day-to-day basis. But why do I do these things? That's what the rest of this talk is about. I want to kind of give you the bigger picture of what I'm thinking about in terms of science and why I'm doing the things that I'm doing. So for the bigger picture, first we'll take a big step back to 30 years ago. So 30 years ago, we knew of approximately 9 planets, depending on how you define a planet. And all of our understanding of how planetary systems form and evolve and what they look like were based on the solar system planets. Now, in the present day, 30 years later, we have about 4,000 known planets, and our picture of planetary systems has completely changed. This is largely due to big missions like Kepler and K2, as well as radial velocity planet searches, which were the first source of known exoplanets. So the picture has changed drastically in the last 30 years. Now, I'm going to assert that in 30 years from now, we will have 100,000 planets known. A lot of these are going to come from continuing efforts with transits and radial velocities, but also from microlensing with WFIRST and from astrometry with Gaia. Gaia is supposed to deliver many, many, many new planets in a different regime than previously. So what is this going to mean for the field? Like, what does the field of exoplanets look like in 30 years with 100,000 planets known? I think one thing we can do to answer that question is look at how things changed from 30 years ago to today. And when we started to find these new planets, one of which was, the first of which was found by someone in this room, actually, we started to see this new regime of planets that we had no idea existed based on the solar system. So we had hot Jupiters, which was the first planet discovered around a main sequence star. We have these super-Earth planets that Kepler found in abundance. There are lots of questions that just came up by looking at the data of what sorts of planets are out there. And with the next generation of surveys and more data that come out, I think that we have a great shot at answering many of these questions. The two that I've bolded here are ones that I'm particularly interested in and planning how to use next generation data sets to answer. But I think that these questions will also, or these answers will also give rise to many more questions. And answering these questions is not going to be easy. So in general, how do we go about understanding planetary systems? I would say that in order to understand planets, actually, we want to understand stars. And the reasons for that are many. So the most obvious one that you're probably aware of is that all current exoplanet detections are done indirectly by studying stars. The most productive methods for finding planets are the transit method, where you see changes in the brightness of the star, or the radial velocity method, where you see changes in the velocity, the Doppler shift of the star. So of course we have to understand stars in order to single out and interpret the signals of planets around them. On top of that, knowing things about the host star gives us better knowledge of the planet that we've found. Because it's an indirect detection, things like the planetary radius depends very sensitively on knowing what the stellar radius is. And a really nice example of this was the planet radius gap that got unveiled in 2017-2018 by a combination of better spectroscopic follow-up of planet host stars known from Kepler and Gaia DR2 parallaxes. So previously, we just saw that there was a general peak in the radius distribution of planets around slightly more than an Earth radius. Now we can see that there are actually two distinct populations here, and this has really interesting consequences for how these populations came to be. It may be saying things about the evaporation of atmospheres off of planets close to their host star and actually giving us information about how the average planet in the galaxy forms and evolves. And finally, one even more subtle connection here is that looking at stars can tell us things about planets because stars kind of represent a fossil record of where the planets formed. To first order, the composition of the star is what the composition of the protoplanetary disk was when planets were being formed. And so we can use information about what the host star is made out of to tell us things about what the planet is made out of. We could even look for even more subtle effects where the act of forming planets or the act of ingesting planets that had been formed changes the composition and the characteristics of the star. So there's all kinds of connections that you can draw between star properties, particularly what they're made out of, and planet properties. So we would like to do all of these things and look at stars at a very detailed level to find planet scale sort of changes in them. And that requires a lot of data to get to that level of detail. So it's a good thing that we are observing a lot of stars in a lot of detail right now. The most obvious example of this, maybe for people in this room, is Gaia. So Gaia is observing billions of stars, and it has many associated ground-based spectroscopic surveys that are also taking advantage of this. So we're learning a ton from Gaia about the layout of the galaxy and the populations of stars within it. We're also getting data on many, many stars from TESS, which launched about a year ago, and this is the NASA's successor to Kepler. It's meant to find transiting planets around all of the brightest stars in the sky. And when you consider the full-frame images from TESS, so not just the pre-selected target stars, but everything that the detector captures, that's 25 million stars across the northern and southern hemispheres. So I'm involved in a project to process these full-frame images and get light curves out of them for all 25 million of these bright stars. And I think this is going to be really exciting in terms of giving us a lot of information about stellar rotation, astroseismology, flares around these stars, all things that are interesting intrinsically for the stars and in terms of their implications for planets and planet habitability around them. But finally, the source of data that I am personally most interested in is all of the stellar spectra that are coming from radial velocity spectrographs. So there are a couple dozen spectrographs at least that are either operating now or soon to be operating. I included a sample of ones with logos, but there are many more that don't have nice logos yet, including the Terra hunting experiment, which CCA is invested in. And all of these spectrographs, most of them are dedicated instruments which get hundreds of nights on their telescope in order to just stare at stars all night long. As a result, they're taking something like all of these spectrographs on any given night are probably collecting 500 spectra of stars, which adds up really fast. And so these spectra represent a great opportunity both to find planets and to learn more about stars, because spectra can tell us a lot, especially in this number and at this resolution.
And that's not multi-fiber spectrographs. So it's
right.
500 one at a time.
Yes, 500 one at a time. It's a lot more challenging to get a stabilized extreme precision RV spectrograph with multi-fibers, but it may be coming. Yeah, so we have a lot of data on stars. We'd like to learn things about stars and planets. How do we do that? What I do mostly in my research is use these really rich data sets to tackle these hard questions about stars and planets. And in particular, in this talk, I want to focus on a couple of examples of things that we can do with large data sets to look at subtle effects that are of interest. The two things being searching the compositions of stars and trying to resolve planet-scale differences in between them to see what's different about stars with and without certain types of planets. And work that I've been doing recently on radial velocity data analysis and the search to find the next Earth-like planets. So the first of those topics was the compositions of stars. And the question that I'm asking scientifically is, do stars with different compositions host different types of planets? You can formulate that in quite a lot of ways. And so I think we're not quite at the point where we can give a definitive answer to this question. But it breaks down into more subtle, into smaller things that we can do, like are stars, if a star is a given age and a given general metallicity and from a given part of the galaxy, does it look like all other stars from that area? In other words, are the building blocks of planets everywhere in the galaxy approximately the same? Or does a star that has a hot Jupiter have anything really different about its composition? So in any case, whichever one of these sub-questions we want to ask, the challenge in answering it relies on measuring the abundances of these stars at a really detailed level, like 1% uncertainties on the abundances of a whole bunch of different elements for these stars. So how do we do that? I'm just going to sort of give a little refresher, because although many of you probably know something about this, you maybe haven't had to think through the details for quite a while. So just to make sure we're all on the same page, how do you go from a stellar spectrum to an abundance determination? So here's an example of a few different stellar spectra all stacked together. What do I do with that? The first thing is to measure the amount of absorption in various lines that correspond to elements that we know about. And so the standard way to do this is equivalent width measurements. This is kind of old school, but it's very effective. It's insensitive to instrument and rotational broadening of the star for the most part. And we can use this both to get the detailed abundances of the star and to measure the iron lines in different ionization states and use that to get the bulk parameters like temperature and surface gravity of the star. So if I have these equivalent widths measured for each of these stars, how do I turn it into abundance measurements? The answer is the magical curve of growth, which translates between these two. And the curve of growth is a distillation of a stellar atmospheric model that tells you the pressure and temperature at different parts of the atmosphere, and therefore allows you to solve the Saha equations and all of this stuff that give you the information about what number of atoms gives rise to a certain amount of absorption under those physical conditions. So if you have a great stellar model, you have a great curve of growth, and you can do this easily. In reality, none of our stellar models are quite good enough to do this perfectly, and so the vast majority of the uncertainty in determining stellar abundances comes from that step, going through the curve of growth and introducing the model. Model atmospheres make a lot of assumptions. They assume local thermal equilibrium. They neglect convection, anything that happens over spatial scales of the star, anything that happens in the time domain on the star. They neglect magnetic fields, rotation, mass loss, all of this stuff. And we know that this is an issue. It's good enough for first order measurements, but when we want to go down to the 1% level of precision, this isn't quite going to cut it. And we see the results of this looking at different findings in terms of what is the abundance of a star versus the the spectral class that the star belongs to. And so these are different elements from different studies, and all of them show that as you go as a function of the stellar effective temperature, the abundance that you pull out from the equivalent width is very systematically different, to the extent that you really can't explain this by physics. It's that you're moving through the grid of stellar atmospheric models to different effective temperatures and different physical conditions, and the wrongness of those models is mapping into the abundances that you get out. So I know this is a bit of a complicated slide, but if you'll trust me, the best models that we have now are essentially still giving us wrong answers at the level of 0.1 dex or 10% or something, which is, we would like to get an order of magnitude better than that. So we're in a regime where we have a lot of stellar spectra, we have really good data, but we don't have great models, and that's our limiting factor. So one thing that we can do to get around this is to use this twin star differential spectroscopy technique. And the idea behind this is that if you measure these equivalent widths for a bunch of stars that all have approximately the same effective temperature, same surface gravity, and same bulk metallicity, so the same opacity in their atmosphere, you can use the same part of the stellar model grid to characterize all of these stars. And that means that you're introducing a minimum dependence on the stellar model because you're directly differencing what you get for one star with that model to what you get with another star with that model. And so you're essentially like, both stars, the abundances are going to be wrong, but they're wrong in the same way. Unlike when you moved to a different part of the grid, to a different stellar temperature, and you got a systematically different wrongness in the model. So if that makes sense, we showed that we can get down to 0.01 dex or 2% precision using this technique. And this figure is just from work that I did validating this using solar spectra and treating them as different stars. So you expect to always get exactly the same abundances, and you do to within the uncertainties that are mostly set by the number of lines that we have to measure for these elements. So having validated that, I went out and used this large data set of solar twin spectra to compare all of these solar twins to the sun and get these percent level precision abundance measurements for them. So all of these data come from the HARP spectrograph. They were part of this large radial velocity planet survey, which I actually did a lot of work on designing and operating this, and that's where most of my 100 nights of observing come from also. We found some exoplanets, which I led, but I'm not really going to talk about that part of it. What I'm going to talk about is what came at the end when we had 50 or more spectra for each star, and we were able to stack up and co-add these spectra and get these just amazing quality lines to measure using this differential equivalent width technique. So we got some really cool results from this. One thing that I was able to find are these galactic chemical evolution trends where stars of different ages from our sample have systematically different abundance patterns for different elements, and these correspond approximately to what we would expect from galactic chemical evolution. So recently Melissa Ness has done some of this similar work using a larger but less precise sample of red giants, and she finds exactly the same trends in that data set, which is a really nice connection there between this solar neighborhood and the galaxy at large. So I think this is really a promising avenue for galactic science. But what about exoplanets?
What's GD? We're in the back row where we don't know our periodic table.
Gadolinium, yes.
Monroe knows.
Yeah. Yeah.
So these are ones that are, because you have only very specific wavelength range, right? These are surveys, is it only always around 6,000 angstroms? Whatever element has lines in that range, right? Is that something that people control?
It's a pretty wide range around 6,000. So the HARP spectrograph goes from 300 nanometers to about 700 nanometers.
So what I don't remember about gadolinium, is it our process?
It is.
Because I mean, the alpha process guys you expect to go together, right?
Right.
Sodium and magnesium and silicon.
Right.
But
Well,
then, you know, nickel,
zirconium is
Is iron.
our
Right.
process, and
right?
it doesn't go with that.
And
So
yet-
I think it's us process, but I'd have to check.
Okay,
And I should also mention this is just a sample of the elements that we have that I picked pretty randomly. So we have 30 of these sort of plots in total, which apparently is too many for me to be on a first name basis with all the elements.
According to Jennifer Johnson, it's S process.
Great.
Do you have our process elements in there?
Yes, we do,
That's
yeah.
really interesting because there was this, competing two papers, actually. One that just came out in Nature that suggested actually collapsars and GRBs might be the main source of our process elements by Brian Metzger. And then now there's another paper by Enrico Ramirez who suggests that actually it can't be. And so he's using the kind of spread of iron versus alpha elements versus our process elements to constrain sources. So
Yeah,
whatever kind
yeah.
of, with those beautiful precision data that would be great. So you have more our process elements in your sample.
Yes, we do. Yeah, and it would be great to talk
And
more
then-
about that.
and that I think
Yeah.
really, because I think there's a very interesting constraints on the amount of mixing that takes place.
Mhm.
Because if they all generated neutron star mergers, they're relatively rare. And then the fact that you have a pretty tight correlation means you have to mix over a pretty large, So anyway, I think
Right.
our
Most
process,
of casket too, so you have to
no, that's why that small scatter is telling you something.
Right. Yeah, so clearly these data have a lot of applications. In the exoplanet world, one thing that people tend to be really interested in is the carbon to oxygen and magnesium to silicon ratios, because if you use the host star as sort of a blueprint for the raw materials that went into the planet, these particular ratios set things like what the atmosphere may be made of, and in particular what forms of rocky materials will be on the surface of the star. And so in the past, these sort of gray points in the background are from similar works that had looked at large samples of FGK stars in the solar neighborhood to see what the spread of these ratios are. And they concluded that there's quite a large difference in these elements, and that means that planets throughout the solar neighborhood may have considerably different abundance, considerably different properties to each other. And this has even been interpreted in terms of whether or not they might have plate tectonics on them, because that can be set by magnesium to silicon setting, whether it's different molecular features. But we find actually that all of the stars that we look at have these ratios within 10% of the solar values, which puts some constraints for models of what bulk compositions of exoplanets might potentially look like and what the range of planets could be out there. Finally, we also tried to link up the bulk abundances of stars with their planetary systems. And this is still very much work in progress, because in order to fully interpret this sort of stuff, we really need to know a lot more about the planets that are around these stars than we are currently able to do. But without going into too much detail on this complicated long story sort of slide, the summary is that we can see from these precision abundances that many sun-like stars have more rocky material in them than the sun does. And this may be linked to either rocky planet formation or the ingestion of rocky planets. which is something that Sem-Young Oh has done some really great work on recently, comparing stars in twin pairs and seeing these sort of signatures on them. So in general, this kind of high precision abundance work is really promising down quite a few different avenues. And I think that it'll continue to be like a great byproduct of radial velocity planet searches, which naturally produce all of these spectra for us to take advantage of. But I do want to turn a little bit to the radial velocity planet searches themselves. So I said that all of the spectra that I was using came from the HARP spectrograph, which is a dedicated, extremely well-stabilized spectrograph meant for hunting for radial velocity planets. And many more of these instruments at even better precisions are being built now, all with this goal of finding Earth-like planets around Sun-like stars. In order to do this, the challenge in the data is to take these spectra that we get and measure Doppler shifts at the amplitude of 10 centimeters per second, or even less, over the course of the many years that it takes to find an Earth-like planet. So there's tons of infrastructure in the community being dedicated to this work. There are dozens of dedicated spectrographs. CCA is among those who has invested in this project. And every one of these spectrographs wants to get to this level of 9 centimeters per second, which is the amplitude of an Earth around a sun. So here's where we're at right now with the existing generation of instruments. This is a planet around Barnard star, I believe, and the amplitude of this signal is an order of magnitude greater than the amplitude of an Earth-like signal. So it's a challenge, it's a huge challenge right now to pick this planet out of the data. That challenge comes from the precision of the measurements, it comes from the time sampling of the measurements, it comes from combining many different sources of data that may be processed differently. And we want to be able to do an order of magnitude better than this in the future. So I think that this question of how do you measure radial velocities is a very relevant one right now. So let's again go back to basics a little bit just to set the stage here. Say I have a spectrum. How do I measure a radial velocity? So the classic approach is take a line where you know what the rest wavelength is, measure what its wavelength is in the spectrum, and solve for the velocity. This is simple, it works great, but it's not too precise if you just have a couple of lines where you know the wavelength really well. You can generalize this up to using many different lines, and this is the cross-correlation technique, essentially. But again, you can get to very good precision with this because you can use thousands of lines for this, and it is the state of the art for what we do right now. But it does require that you know a lot about the stellar spectrum. So as a result, like often we look at sun-like stars and we use a template that's based on the solar spectrum to do this. But we don't know, like, if you want infinite precision for any given star, its spectrum is unique to it. It has different abundances, different line broadenings than any other star does. And you want to use like a precisely tailored template for that. In other words, we're again in this regime where we have lots of data on these stars, but the models that we use, if we use a traditional cross-correlation technique, are a limiting factor. So let's go data-driven. If we have a bunch of measurements of the same star taken at different times, we end up with spectra that are shifted relative to each other. We could take a guess of what the Doppler shift is, stack them up, and create a data-driven template from that. And this works really well, but the one caveat is that if I shift these back to the stellar rest frame, I want all of the lines to move to the stellar rest frame, which will happen if they're from the star, but they're not all from the star. So if you notice, like over here, there are a couple of deep lines that are not moving along with along with the star. They're all stacked at the same place in the observatory rest frame, and that's because they're telluric lines from the Earth's atmosphere. So naively producing a data-driven template like this will fail in the region where there are lots of telluric lines. And that's not a huge deal for this particular data set where there aren't that many telluric lines, but it will become a big issue for the near-infrared spectrographs that are coming online these days.
So there's no way to remove them by observing standard stars?
You can observe standard stars. That takes a lot of telescope time that we would like to be pouring into the radial velocities, and it's also not perfect because you have to, dividing out the standard star can't actually be done perfectly, and Sharon Wong has done some really good work on this, illustrating that. Yeah.
Is there a way to just mask them?
Yeah, so you can currently, if you use like a cross-correlation technique or something, you can just drop areas where you know that there are telluric lines. And we do know the telluric spectrum fairly well, so that's very feasible to do. But it's dropping information that you could be using to get these precise radial velocities for which we want like every single line that we can possibly get. And it's just not going to be possible in the near infrared again because there's tellurics everywhere there, and so you'd mask out your entire data set. But yeah, those are both good techniques to use, and people have used them to much success. So I wanted to try something a little bit more sophisticated, but not that much more sophisticated. This is actually a really simple data-driven model that I implemented as this Wobbly code that I'll be telling you a little bit about. So basically, I'm saying that the flux in any given spectral pixel can be represented by the star's flux and the telluric line flux. And so I'm actually working in log wavelength because these are multiplicative factors and they add in log, and that makes putting it into log and making it additive makes it a lot more tractable. But essentially what I'm doing is I'm saying I have a template for what the stellar spectrum looks like, and that's just a bunch of free parameters that I'm going to solve for. I also have a template for what the telluric spectrum looks like, and that's also a bunch of free parameters that I'll solve for. I'm also going to solve for the velocity of the star, putting in a Doppler shift structure to it. And if I have enough data, I will also solve for sort of a PCA-like representation of low-dimensional variability in the telluric spectrum. So this is quite a lot of free parameters. It's order of 10,000 or something. But we have even more data points, like order of 1 million. And so this is a really simple, easy to understand, easy to interpret model that that is not so simple to actually implement, but luckily we have really great people like Dan Foreman-Mackey here who know a lot about TensorFlow, and so together we were able to implement this in a very fast, tractable way to do these optimization problems, and got pretty good results. So this is just an example of the fit to the data. This is around the H alpha line here. So black are the data points, red is the prediction for the stellar model, and blue is the prediction for the telluric line model. And you can see that the lines separate out very well. In some cases, you find telluric features that you wouldn't really have been able to pick out by eye in the data using this. So you wouldn't have known maybe to mask these lines. It fits the data quite well. But do we believe that these particular lines do truly belong to the star or to the tellurics? So one test that I did to validate this is I independently ran this model on 2 very different data sets, one being the Sun-like star 51 Peg, where the very first exoplanet was found, second one being the bright M-dwarf Barnard star. They have super different underlying stellar spectra. They also have different data properties. Barnard star was observed at lower signal to noise because it's fainter. But solving for these 2 independently, we get exactly the same tellurics model out of them, which is very promising. and kind of validates that we are truly able to pull out the tellurics, even in a case where you can't obviously see that they're there. Similarly, I did some tests on the radial velocities. So this is a comparison of the RVs that I get using Wobbly, this code, to what the standard HARPS pipeline gets for 51 peg. So we recover the planet. And for Barnard star, we recover the linear trend in the radial velocities, which is actually due not to a planet or a companion, but secular motion, because Barnard star is moving so fast across the sky that you can actually see the projected radial velocity changing, which I think is really cool. We get a slightly better precision in the radial velocities for Barnard star than the standard HARPS pipeline does, which is not surprising because the standard HARPS pipeline is not super well optimized to working with M-dwarf stars. For 51 peg, which is where the HARPS pipeline performs best, we match the precision and get the same answer. A lot of work went into this code, and it all went out in the open. This is a piece of open source software, and it's one of the very few open source codes for doing this sort of precision radial velocity work. It's available on GitHub, and I've had a lot of positive feedback about it from the community, which is really nice.
So you came up also with the name
Wobbly, yes. You can ask me after why.
At the end. Was it
The accent is implied. It also turns out is a really good way to get people to talk about your code if you give it a silly name. I've been told that entire conferences were like devolved into debating how you pronounce it. It's great. So why Wobbly? I think that it has quite a lot of benefits. It's open source, which I think is great given the number of new radial velocity spectrographs that are going up right now, where people don't necessarily have like a legacy code that they use to extract radial velocities. It's good to have something that works well that the community can just adopt and use as either use as their pipeline or use as a benchmark comparison for their pipeline. It's written in a very simple and interpretable way, and I think this makes it really good in terms of using it to experiment with different data-driven techniques. So we did this with the telluric lines. We added in telluric variability in different ways and settled on what worked best, and we're able to see it very obviously in the data, what's going on and how to interpret what's going on. Yeah.
Sorry for the pessimistic question, but what happens, how does it behave for a stationary star?
Yeah, so we did do this for some RV standard stars, and it gets, it does what all other pipelines do, which is it gets that the RVs are a straight line to within some degree of scatter. I think the issue is that there is truly no such thing as a stationary star, and it's hard to say what the actual precision is when you're validating from these standard stars, because even the standard stars might have planets or stellar variability at some level.
But it doesn't get caught up in trying to distinguish tellurics from real lines.
Oh, right.
When it's stationary.
Right. No, good. That's a good point. So no star is actually stationary from the perspective of the tellurics because of the barycentric shifts of the star. And so if the star moved at exactly the barycentric shifts and always overlapped the tellurics, this method would not work, but that would be a hell of a star.
Or if it was at the pole, right? It would also fail if it was exactly at the ecliptic pole, which isn't that where TESS is spending its time? Isn't the continuous viewing zone of TESS exactly where Wobbly won't be able to separate?
But there's also a geocentric direction, which is the celestial pole. So.
Yeah.
Oh, yeah.
Meter per second is really
geocentric,
small.
Yeah. Fine.
Yeah. I think it would have to be very
It would have to be
an
an adversarial binary would kill you.
Sure, yes. I agree.
So can you use the Tolerex as a calibrator? So to add a parameter in and?
Yeah, you can, and we're looking into doing that for spectrographs like Keck-Hyras, where we expect that they're not super well stabilized. You might be able to fit explicitly for the velocity of the Tolerex
Right.
and use that as sort of the instrument velocity.
Yeah, and so more generally, have you thought about, right now you're modeling the photons coming into the detector, but to sort of model the whole system,
Yeah, we would
And
love to
one-
do that.
Particularly for THE, where you're gonna,
Right. Yeah, no, I think the dream is to not be working with an extracted spectrum, but to actually be modeling the entire CCD. And this was, we're a ways away from being able to do that, but we did write down this model in such a way that it wouldn't be difficult to scale it up to an extra dimension in there. So that has been in the back of my mind for a while. One nice thing about Wobbly is that it's kind of this experimental platform, and I just throw up here that we got this to work pretty well for Tellurix, and next we're going to do stellar variability, which is actually like the thing that I would be spending the entire talk talking about if I were talking to RV people, because this is what is on everyone's minds. So remember how I said that we have to study stars to understand planets? The variability of the stellar spectrum is a huge reason why we really need to understand stars better. Because stars do all kinds of funky stuff. The intrinsic stellar spectrum is constantly varying in subtle ways. There's star spots and plages, there's convection, convective overturn, there's granulation, there's astroseismic pulsations. A lot of these things are things that we need to be able to disentangle from the radial velocities in the data. And if we can't figure out how to do this, a lot of these next generation radial velocity spectrographs that are looking for Earth-like planets, where tons of money and resources and person hours have gone into making these super instrumentally precise, a lot of this will not live up to its full potential if we don't have a way of dealing with the intrinsic stellar variability. And so that's one thing that I am really excited to work on in the domain of Wobbly and other data-driven domains, because we do have the amount of data now that we can really start to tackle this in various ways. So on that note, I just want to say that we have had a lot of success recently with having people come to CCA from the extreme precision radial velocity community. And we recently had this telluric line hack week session that was extremely well attended and ended up with lots of new projects sprouting up. And I learned a ton about how to make Wobbly better for the community and better serve people who are using it in different instruments. And it seems to be getting a lot of traction in that sense. So I would love to see CCA continue to kind of play a role in bringing people from the RV community together, because I think it's really going to take everyone together to solve the major issues of data analysis that are facing us right now in terms of stellar variability and other things. This is going to be a sort of a long-term project to tackle this and to deal with it, and CCA is a great place to invest in these sorts of long-term, somewhat experimental projects. And CCA has an existing investment in the Terra hunting experiment that we really want to make use of. So I think that CCA is in a place where we could make a huge impact on this EPRV field. And we could be a great resource to the existing EPRV community and help everyone make their codes and analysis and observational strategies better. So just to loop around to where I started from, let's say that we do solve radial velocities. We get tons of planets down to 9 centimeters per second precision. What does that mean for the overall picture? I said that we would have 100,000 planets in the future. What is the role of radial velocities in this? What is the role of stellar spectroscopy and precision techniques here? I think that actually radial velocities slot right into this overall picture really neatly and are a critical part of it, because transit techniques like with TESS and Kepler and K2 are great for finding short period planets because signals are larger and occur more frequently, and the inclination effect, the geometry means that you're more likely to find the close-in planets for transits. So they're great from that aspect. Astrometry is great for the long period planets, and Gaia will probably deliver tons of Jupiter analogs. But this intermediate regime of Earth analogs is not really going to be touched by existing missions in either of those spaces. And so I think that RVs are really key to finding Earth-like planets and sort of filling out the planet census. And they deliver really detailed information about stars and stellar compositions that we can't get in other ways, and which are directly complementary to the information that we get from, say, light curves of rotation and pulsations and things with TESS, and with the bulk stellar properties and sort of the population level knowledge of stars that we get from Gaia. So I think that one thing that the exoplanet and stellar communities have learned is that having many complementary techniques kind of reveals more information than the sum of their parts. And I think that RVs will be really key in slotting into this bigger picture of planetary systems in the future, and will be highly complementary to Gaia and Sloan and other things that we're all thinking about here. So I will just leave up my takeaway points and take questions.